Relational model versus document model. The best known data model today is probably that of SQL, based on the relational model proposed by Edward Codd in 1970. Data is organized into relations called tables in SQL, where each relation is an unordered collection of tuples, rows in SQL. So this is the key idea. It's actually an ordered collection of rows, while the document database is a collection of data documents. The relational model was a theoretical proposal, and many people at the time doubted whether it could be implemented efficiently. However, by the mid 1980s, relational database management systems, RDBMS, and SQL had become the tool of choice for most people who needed to store and query data with some of regular structure. So these are the tool of choice in 1980s for storing and querying data. Remember, databases are actually used before directly by the client. So whenever you go to an airport, you actually have to initiate a request to this database storage and receive a response from it. The roots of relational database lies in business data processing, which was performed on mainframe computers in the 1960s and 70s. The use cases appear mundane from today's perspective, typically transaction processing, entering sales or banking transactions, airline reservations, stock keeping in warehouses, and batch processing, customer invoicing, payroll reporting. Other databases at that time forced application developers to think a lot about internal representation of data in the database. The goal of the relational model was to hide that implementation detail behind the cleaner interface. Over the years, there have been many competing approaches to data storage and querying. In the 1970s and early 1980s, the network model and the hierarchical model were the main alternatives, but the relational model came to dominate them. So the alternative actually is a network and hierarchical, which we will discuss later or in the future videos, just to give you an idea what are the alternative options back then, because it's important to understand history, because the modern document database also got or learned from a lot from those alternatives, and there's a lot of effort that has been poured into those alternatives as well. Object database came and went again in the late 1980s and early 1990s. XML database appeared in the early 2000s but have only seen niche adoption. Each competitor to the relational model generated a lot of hype in its time, but it never lasted. As computers became vastly more powerful and networked, they started being used for increasingly diverse purposes. And remarkably, relational databases turned out to be generalized very well, beyond their original scope of business data processing, to a broad var- variety of use cases. To a broad variety of use cases. Much of what you see on the web today is still powered by relational databases, be it online publishing, discussion, social networking, e-commerce, games, software as a service, productivity application, or much more. So relational database persists. As you notice, with this technology, only few persist over time. So the most common today are actually relational databases, NoSQL, or not only SQL, which is an improvement of NoSQL and a graph databases, which is for social networking, because it is better model to serve for interconnected queries such as Facebook. The birth of NoSQL. A number of interesting database systems are now associated with the hashtag NoSQL, and it has been retroactively reinterpreted as not only SQL. There are several driving forces behind the adoption of NoSQL databases, including a need for greater scalability than relational databases can easily achieve, including very large datasets or very high write throughput. So we see that before with Firestore. So for the live kit that we discussed before, it's actually using a high write throughput database or a document database model called Firestore. A widespread preference for free and open source software over commercial database products. So these are the needs that make this NoSQL prevalent. There is a need for a free and open software, which Firestore MongoDB provides specialized query operations that are not well supported by the relational model. So MongoDB is better in search for with Firestore, but Firestore is better than common relational database. Yeah, MongoDB, which we discussed in our blogging app, is actually better for search because it's better for query operations. That's why we were able to search just a text in our blog app. Frustration with the restrictiveness of relational schemas and a desire for more dynamic and expressive data model. So because our interface nowadays needs more expressive and needs to be less restrictive, the thus the birth of NoSQL data model. Different applications have different requirements, and the best choice of technology for one use case may well be different from the best choice for another use case. It therefore seems likely that in the foreseeable future, relational database will continue to be used alongside a broad variety of non-relational data stores. An idea that is sometimes called polyglot persistence. So because, like we discussed in the previous chapter, a data model usually is a combination of one character to another. So it is likely that we will see a combination of relational and non-relational databases. So we also see that in databases today, just like with PostgreSQL, when you can apply non-relational data format like JSON. You can also do that in MySQL, but it's less expressive, etc. So, yeah, you can also apply some relational characteristics with Firestore and non-relational models such as MongoDB. So they are mixed nowadays, but they are used as with other things. They are used in different purpose. Now we will start with the object relational mismatch. Most application development today is done in object-oriented programming languages, which leads to a common criticism of the SQL data model. If data is stored in relational tables, an awkward translation layer is required between the objects in the application code and database model of tables, rows, and columns. The disconnect between model is sometimes called an impedance mismatch. So because a database actually works as a collection of rows or a collection of documents. It doesn't work as a collection of objects, just like a programming language. Therefore, ORM, that's why we use an ORM before for our MongoDB for our blogging app. So even though it's a collection of database documents rather instead of rows, it still needed an ORM because the collection of objects doesn't fit as well in our database. So that is called an impedance mismatch. That's actually what's making the abstraction, or what's making each layer or integration of a web application harder as we create more complex features. Object relational mapping (ORM) frameworks like Active Record and Hibernate reduce the amount of boilerplate code required for this translation layer, but they can completely hide the difference between the two models. So Hibernate, we actually use that Hibernate in our blogging app. So there's also an Active Record that reduce the amount of boilerplate code required for this translation, but they can completely hide the difference between the two models. We also use ORM in our full stack ESP, so I recommend going back on that. For example, figure 2.1 illustrates how a resume, a LinkedIn profile, could be expressed in a relational schema. The profile as a whole can be identified by a unique identifier, user underscore ID. Fields like first underscore name and last underscore name appear exactly once per user, so they can be modeled as columns on the user's table. So if you have a fields that appear exactly per user, you could think of that as a column in your collection of row in relational database. Now figure 2.1, representing a LinkedIn profile using a relational schema, photo of Bill Gates. However, most people have more than one job in their career positions, and people may have varying numbers of periods of education and any number of pieces of contact information. There is one-to-many relationship from the user to these items, which can be represented in various ways. So if you have the user as having a multiple job in their lifetime, or that's the structure of the data model, because that's just how the reality works. Therefore, what you have is a one-to-many. So that fits on a specific data model, which we will discuss later or in the future video. In traditional SQL model prior to SQL 1999, the most common normalized operation is to put positions, education, and contract information in a separate tables. With a foreign key reference to the user table as in figure 2.1. So this is the traditional approach. You break the related information in different tables and you connect them using the user ID. As you can see, these are all connected via user ID. And the user ID is kind of like the root, and then it has like left root, these three tables, and right root, these two tables. That's the traditional model. Later versions of the SQL standard added support for structured database data types and XML data. This allowed multi-value data to be stored within a single row, with support for querying and indexing inside those documents. So this traditional model has been improved to support other data types, structured data types such as XML data, And this also allowed multi-valued data stored in each tuple, with support for querying and indexing inside those documents. These features are supported to varying degrees by Oracle, IBM DB2, MS SQL Server, and PostgreSQL, which are all relational database. So these storage engines of these companies now support this modern type. A JSON data type is also supported by several databases, including IBM, DB2, MySQL, and PostgreSQL. So just like what I've said, a relational PostgreSQL can be more expressive, or can combine a non-relational data such as JSON and a MySQL as well, but it's less expressive. A third option is to encode jobs, education, and contact info as JSON or XML document. So now we're talking about more of a document data model because we're talking about JSON. Store it on a text column in the database and let the application interpret its structure and content. So this JSON model for MongoDB actually stored as a JSON text, and the Bison or the database of MongoDB are responsible for interpreting that text. It actually stored that by MongoDB as Bison, and let the application interpret its structure and content. In this setup, you typically cannot use the database to query for values inside that encoded column. For data structure like a resume, which is mostly a self-contained document, a JSON representation can be quite appropriate. See example 2.1. JSON has the appeal of being much simpler than XML. Document-oriented database like MongoDB, RethinkDB, CouchDB, and Espresso support this data model. So for this type, actually, a document database is much more appropriate. So the traditional SQL model is not actually being used nowadays. So a document-oriented database like MongoDB, RethinkDB, CouchDB, Firestore are some example of database that can support this type of data. Some developers feel that JSON model reduces the impedance mismatch between the application code and the storage layer. So the JSON or the document data model kinda make the integration or translation more intuitive from application code to database code. However, as we shall see in chapter 4, there are also problems with JSON as data encoding format. The lack of schema is often cited as an advantage. We will discuss this in schema flexibility in document model later. So there's also an issue with translating JSON from application code, right, to a storage layer. But it's less impedant or less resistant to translation than a relational database. The JSON representation has a better locality than multi-table page schema in figure 2.1. Yeah, I think that's much better. There you go. The JSON representation has a better locality than multi-table schema or relational database we saw in figure 2.1. So locality, again, that's related to temporal and spatial locality of OS. If you want to fetch a profile in a relational example, you need to either perform multiple queries, query each table, by user ID. So if you want to load this profile, you need to query multiple data or multiple table to be able to get all those related information. Unlike with JSON, you just need to load one document, and on that one document all the user profile are inside of it, or perform a messy multi-way join between the user tables and its subordinate tables. In the JSON representation, all the relevant information is in one place, and one query is sufficient. The one-to-many relationships from the user profile to the user's position, educational history, and contact information imply a tree structure in the data. So since that's the realistic example in the real world, it's actually more of a tree base than a relational database. Therefore, a JSON representation makes much more sense. So, a JSON representation makes this tree structure explicit. See figure 2.2. Here, many to one and many to many relationships. In the example 2.1 in the preceding section, region underscore ID and industry underscore ID are given as IDs, not as plain text strings. Greater subtle area and philanthropy. So in a relational example, the region underscore ID and industry underscore ID are actually used or represented as an IDs rather than a text string. As we will see in JSON, it will be represented just a text string. Figure 2.1 representing a LinkedIn profile using a relational schema. Photo of Bill Gates courtesy of Wikimedia Commons, Ricardo Stockart, Agency Brazil. If the user interface has free text fields for entering the region and the industry, it makes sense to store them as plain text strings. But there are advantages to having standardized list of geographic regions and industries, and letting users choose from a drop-down list or auto-completer. So there's an advantage on that structure of relational database in which you kind of have like a list options in about face we discussed, in which you avoid user to make mistakes because you have a predefined list, and you also just need to change one thing in the background and all of the user ID will be changed. So unlike a pure text string, it's much harder to change in the future in case something changes. So that's the advantage of relational database. It really depends on how you expect your data to change over time, because as your application grow, your data also need to evolve with that, with your user demand. So here, letting users choose from a drop-down list of autocompleter, consistent style spelling across profiles, avoiding ambiguity, i.e. if there are several cities with same name, ease of updating, the name is stored in only one place, so it's easy to update across the board if it ever needs to be changed. Change of a city name due to political events, localization support when the site is translated into other language. The standardized list can be localized, so the region and industry can be displayed in the viewer's language. Better search, i.e. search for philanthropist in the state of Washington, can match this profile because the list of regions can encode the fact that Seattle is in Washington, which is not apparent from the string greater Seattle area. Whether you store an ID or a text string is a question of duplication. When you use an ID, information that is meaningful to humans, such as the word philanthropy, is stored only on one place, and everything that refers to it uses an ID, which only has meaning within database. When you store the text directly, you are duplicating the human meaningful information in every record that uses it. The advantage of using an ID is that because it has no meaning to humans, it never needs to change. The IDs can remain the same even if the information it identifies changes. Anything that is meaningful to humans may need to change sometime in the future, and if that information is duplicated, all redundant copies need to be updated. So you less likely have to maintain a duplicate information if you have that relational database characteristics. So the core idea, using IDs instead of human meaningful strings avoid duplication and avoid expensive fan out or on write or fan out on read updates. This idea applies across database design, distributed system, timeline fan out, Kafka workers, quick video delivery, real-time chat, tail latency, and microservices. So remember our discussion with Twitter. You are less likely to make mistakes in fanning out on write for your followers and fanning out on read for your followee if you will implement this type of characteristics in your system. So let us connect it system by system. First, database modeling. Why IDs avoid tail latency problems? If you store, why is it like this? If you store text directly in many rows, your updates require rewriting millions of rows. Rewrites create huge write amplification, cache invalidation, replication log, inconsistent reads, tail latency spikes, P99 to P999. Example, tweet 1, topic name, philanthropy, tweet 2, topic name, philanthropy, tweet 3, topic name, philanthropy. If the topic name changes, you update millions of tweet rows, huge fan out on write, huge tail latency, long compactions, long dynamic partitions, hotspots. Second, storing IDs remove this entire problem. New table. Topics, ID equals to 55, name equal philanthropy. Tweets for tweet 1, topic ID 55, tweet 2, topic ID 55, tweet 3, topic ID 55. If the topic name changes, only one row changes. All tweets automatically read the new name. No fan out rewrite, zero tail latency amplification. Third, how this connects to Twitter or TikTok or Meta timelines. All big systems never duplicate user-facing strings in timeline rows. Timeline events store user underscore ID, tweet underscore ID, topic underscore ID, media underscore ID, video underscore bitrate underscore ID, author underscore ID, region underscore ID, device underscore type underscore ID. Because duplicated string cause large Kafka messages, large Redis timeline entries, more network I/O, more memory, more cache misses, more tail latency. ID references enable cheap fan-out workers, small Kafka events, small Redis ZSet objects, fast DynamoDB reads, efficient cache hydration, zero copy on write when metadata changes. This is what real-world timeline systems do. How it relates to fan-out on write versus fan-out on read. If you store text directly, each timeline entry becomes large. Fan-out worker push fat objects into user timelines. More memory, more CPU, more network. P99/P999 latency increases. Back pressure causes tail latency amplification. If you store IDs, every fan-out event is tiny. Like this, tweet ID colon 987, author underscore ID colon 22, topic underscore ID colon 55. So that's with open and close, semi-curly at the start and at the end. Redis ZAD timeline colon user ID timestamp tweet underscore ID. Your entire system becomes smaller, faster, latency resistant, easier to rehydrate from Kafka. Fifth, how disconnect to quick CDN's YouTube EBR. This is huge. YouTube stores video underscore ID, stream underscore ID, bitrate underscore ID, not literal strings like 1080p to stream to 2025 to VBR to AUC. Why? Because bitrate underscore ID stays fixed even if the underlying representation changes. This enables rewrite new video encodings, swap new HLS slash dash manifest, no redoing user references, no fan out updates, no tail latency spikes. IDs support atomic metadata swapping. How disconnect to percentile monitoring HDR histogram. Digest. Duplicate data, larger writes, more variable latencies, fat tail P999 spikes, Kafka throughput increases, DynamoDB partition hotness increases, Redis ZSET latency increases, network queues increase, kernel scheduling delay increase. These spikes are captured by HDR histogram T-digest forward decay because they efficiently measure tail latency. IDs reduce message size, less queuing, lower jitter. DB writes, fewer stragglers, fewer P999. CPU per request, less thread contention, cache misses, stable latency. How disconnect to WebSockets slash web transport slash chat apps. Real-time chat, Messenger, WhatsApp, Discord. Messenger stored as message underscore ID, sender underscore ID, conversation underscore ID, content underscore ID, media underscore ID, not duplicated strings like username. Because contact change names, group change names, username change, photos change. If strings were duplicated, every rename, rewrite millions of rows. Tail latency explosion, outages. IDs avoid this. How this connects to AWS services. DynamoDB, you store IDs, not full objects. You only fetch expanded objects once through. Docs, Elasticache, Lambda read through cache, CloudFront Edge caching, Kinesis. Records are small because you send IDs. This reduces shard latency and increases throughput. Lambda, fan out workers process tiny payloads, equal cheaper plus faster. CloudFront slash YouTube CDN. IDs allow cacheable paths, atomic rewrites of metadata, stable URLs, zero invalidation of millions of objects. Summary that ties all threads together. Duplicating human readable strings causes fan out on write updates, causes P99 to P999 tail latency, increases Kafka or Redis or DynamoDB pressure, breaks real-time systems like chats, makes ABR video manifest brittle, makes CDNs require massive invalidations. Using IDs, remove unnecessary writes, remove tail latency amplification, makes fan out on chip, keeps timeline small, keeps CDN URL stable, allows quick or ABR to work smoothly, makes percentile histogram stable, prevents microservice cascades. This rule is one of the deepest universal principles connecting database design, distributed systems, real-time messaging, video streaming, quick fan-out architecture, tail latency. Everything we discuss ties back to this: never duplicate mutable data, always store IDs. So that incurs overheads and risk inconsistencies where some copies of information are updated but others aren't. Removing such duplication is the key behind normalization in databases. So that's actually the concept of normalization and denormalization in database. Database administrators and developers love to argue about normalization and denormalization, but we will suspend judgment for now. In part 3 of this book, we will return to this topic and explore systematic ways of dealing with caching, denormalization, and derived data. Unfortunately, normalizing this data requires many to one relationships. Many people live in one particular region, many people work in one particular industry, which don't fit nicely into the document model. So if we normalize that actually this LinkedIn profile, the data requires many to one, like many to live, so which don't fit nicely into a document model. So we kind of have to choose or balance that because we want it to be easily changed to avoid the latency, and normalize the data using this user ID. But at the same time, we also need to get the advantage of document data model. In relational databases, it's normal to refer to rows in other tables by ID because joins are easy. So as we saw, this relate to these three tables by ID because joins are easy using those connections. Now in document databases, joins are not needed for one-to-many tree structures, and support for joins is often weak. Since you load that entire profile in one document, you don't need the joins, and support for join for this data model are actually weak. So you can easily join that from like one profile to another. If the database itself does not support join, you have to emulate a join in application code by making multiple queries to the database. So if you're using document database models such as JSON, you will have to do the join in your application code, such as if you're using React with Next.js, you will have to do the joins of your document in Firestore. In this case, the list of region and industry are probably small and slow changing enough that the application can simply keep them in memory. So in this case, the list of regions and industries are probably small and slow changing enough that the application can simply keep them in memory. So your application can just keep them in memory, this joins, since it's just a small, you don't need as much memory. But nevertheless, the work of making the join is shifted from database to the application code. Moreover, even if the initial version of an application fits well in a join-free document model, data has a tendency of becoming more interconnected as features are added to application. So a small part of your development, it may be enough to store that joins in memory. But as your system grows, just like Facebook, data has a tendency to be more interconnected. That's where the graph database of Facebook comes in. For example, consider some changes we could make to the resume example, such as this. The company name is not just a string, but a link to a company entity. Screenshot of LinkedIn. So as you can see, the company name, you can click on that. That will route you to the actual company's website. So it's interconnected. Organizations and schools as entities in the previous descriptions. Organization, the company where the user works, and school underscore name, where they studies, are just strings. Perhaps they should be references to entities instead. Then each organization, school, or university could have its own web page with logo, newsfeed, etc. So previously, the organization and school are just strings. So now we were referencing them as an entities because they link to an entire web page like this. Before it's just a string of Microsoft. Now we're linking them to an entire web page. So then each organization, school or university could have their own web page with logo, newsfeed, etc. Each resume could link to the organization and schools that it mentions and include their logos and other information. See figure 2.3, example from LinkedIn. Recommendations say you want to add a new feature. One user can write a recommendation for another user. So let's say you want to recommend something to another user. So that's another type of many-to-many or data being more interconnected. The recommendation is shown on the resume of the user who was recommended, together with the name and the photo of the user making the recommendation. So aside of making this interconnected, you also need to normalize the data, because if the recommender updates their photo, any recommendations they have written need to reflect the new photo. Therefore, the recommendation should have a reference to this author's profile. Figure 2.4 illustrates how these new features require many-to-many relationships. The data within each data rectangle can be grouped into one document. But the references to the organization, schools, and other users need to be represented as references and requires joins when queried. So as you can see, the data within each dotted rectangle can be grouped into one document, but the reference to organizations, schools, which is outside, are actually represented as references to normalize the data and require joins when needed. So this is the blended approach that takes advantage of relational data model and a document data model.